Alright, so we'll start with getting all of our forces and moments in Cartesian form. So, I'll look for my forces. I'll draw them in green. Here's a 10-pound force right here. We'll call that force 1. And that's really easy. That's just in the negative z direction. It's only going downwards. It has no x and no y component. So its Cartesian form right out is going to be this right here. Just never forget, make sure when you write your numbers, you look at the picture and you're getting the correct sign. I see a 6-pound force over here. We'll call that force 2. And it looks like that force is only going in the y direction. It's pointing in the positive y direction. It's not going in the x, and it's not going in the z at all. So those components will be 0. Alright, so that's positive 6. It's 6 in the positive y direction. And we'll have a force going this way. That'll be force 3. And another 6.601 force going this way. That's force 4. So here's force 3 and force 4. Now technically you won't be wrong leaving it like this, but what I've seen some people do is just write these together as the couple moment that they form. Notice that these two are couple forces. Two forces that have the same exact strength, the same magnitude, and they're in complete opposite directions. And the reason why, some people just bunch these up into one couple moment is that the reason why we're writing out all of these forces in vector form is that what we do a lot of times in statics is we add up all the forces acting on an object. And in statics, that's equal to 0. So when you add up these two forces, they will completely cancel each other out. They will add up to make 0. So this pair of couple forces won't even play a role, have any effect in my sum forces, any of my sum forces equations. So for that reason, they really don't play any impact in terms of force, but they rather create a couple moment. So let's go ahead and create and draw out the couple moment that these two forces create. And even though we're in 3D, I'm going to use the 2D approach for calculating couple moments, because it's very easy to tell what that perpendicular distance is in between these two couple forces. So D is simply going to be 2 feet. And of course, each one of those forces is 6.601. So the magnitude, the strength of this couple moment will just be 13.2 pound-feet. So we have the magnitude of this couple moment, but now we have to determine the direction. And since we're using the sort of scalar equation for couple moment, we have to determine the direction ourselves by visualizing this. And it can get a bit tricky, but here's how you do it. So imagine putting your left hand right here and your right hand right here, and imagine sort of rotating this box just like those forces are. Your left hand's going to create this force and push that way, and your right hand's going to push this way. If you do that, you're going to want to rotate the box like this. And remember, a moment vector is always going to be perpendicular to the plane of rotation. So the plane of rotation is the xz plane. And to figure out whether it's going to the left or going to the right, you use the right hand rule. So take your right hand and curl your fingers in the direction of this rotation arrow. And you'll see that your thumb is pointing this way. And that way is in the negative y direction. So the direction of this couple moment is purely in the negative y direction. But if you didn't want to use that 2D approach to calculate this couple moment, you could do the vector approach for calculating a couple moment, which is more straightforward but takes a little longer. couple moment is r cross f. My r could be c to d, c to b, it could be e to b, but so that's my r. Could be, it's basically from one force to the other force, and the force that you use is the one that your r ends up on, so it would have to be this top force 3 in this case. But you could carry out the cross product and get the same thing as well. So moving on with our forces, we have this 8-pounder right here. Looks like this force is only in the zy plane. So if I figure out this angle right here, I can figure out my two components. It's really a two-dimensional force. So this length right here is 6 feet. This length is 2 feet. So if I do inverse tangent, I'll get 18.4 degrees. So if I do 8 times the cosine of 18.4, I'll find this one. That'll be a y component. And if I do 8 times the sine of 18.4, I'll find this component right here, and that looks to be a positive z component. Remember, this is just a basic right triangle right here that we're working with. So here's my sine and cosine. I calculate my fz and my fy. Just always remember, put that sign on yourself. So let's write out our Cartesian form for this one, and we'll call it force 5. So that's it for my forces. Now we'll move on to our moments. Start with this one right here. I know this is a couple moment because regular moments depend on the point that you're calculating the moment about. Only couple moments can be drawn freely, like this, because the couple moment is the same regardless of what point you're taking moments about. A couple moment will be there. And it looks like this couple moment is right in line with this line here. So it looks like this 30 pound-foot couple moment is only in the negative x direction. And we'll call this couple moment 1. And we'll have a couple moment 2 right here. And that looks like it's going in the positive x direction. And it's only going in the x direction. So that's it for part A right there. So part B, we want the moment of the 8-pound force about the coordinate axes. So that just means the x, y, and z axes. So we have to pick a point that's on all these axes and then do r cross f, where r is from that point we've chosen. That'll be the origin, because the origin is the only one on all 3 axes. The moment is r cross f, and r will be from this point right here to any point on the line of action of our 8-pound force. Here's our 8-pound force right here. So our r could be r from origin to A, or it could be r from origin to D. Just pick the simplest one. I think r from origin to A would be the simpler one. So we'll write ROA, so r from the origin to A, crossed with that 8-pound force, and that's our force 5. So let's assemble our position vector, ROA, first. You don't need super complicated math to do this. If I go from O to A, I know I'm going to walk 2 feet in the positive x direction. So this is going to be 2I. And when I walk from O to A, I'm not going in the y direction or the z direction at all. So 0 j hat and 0 k hat. Alright, so we got our position vector OA already. Our force 5 is already in Cartesian form. So now we just have to carry out the cross product. So I have to carry this out. I cover up this row and do this product minus this product, and that'll just be 0. So 0 I hat. Now I cover up the j and do 2 times 2.5 minus 0 times 0, so that's just going to be 5. But don't forget, whatever you get here, you got to put a negative on it. That's just how the cross product works, for whatever reason. So negative 5j hat. And lastly, I cover up the k, and I do 2 times 7.6 minus 0 times 0. That'll just be 15.2 k hat. And that is our couple moment from force 8. So let's backtrack for a second. They wanted the moment of the 8-pound force about the coordinate axes. So we use this point O here because that is the point that's on all the axes. So what they really want is the moment about the x, the y, and the z directions. So here's the moment about the x, moment about the y, and moment about the z directions. So that's that. We don't need to do anything else with this question. Now part C, moment about the 10-pound force, moment of the 10-pound force about line OC. So here's line OC right here. And my 10-pound force is force 1 right here. So we want the moment of this force about that line. Well, the way you do this is, actually this is the exact same concept that we just did. Pick any point on this line, and you make a vector from that point to any point on the line of action of your force. I mean, we're essentially doing R cross F to calculate the moment. It's just that this R here, R must be from a point on this line, any point on this line, to any point on the line of action of F1. Any one of these infinite possibilities could be your R. And just choose the one that makes your math the simplest. So I want to pick O. I'm going to go from O to A, because that is honestly just the simplest I can think of. And plus, we already figured it out from last time. So ROA cross my 10-pound force. That's force 1. So we can easily perform our cross product here and figure out what that moment is. And again, don't forget, when you do the j part, this is negative 20 minus 0, which is of course negative 20, but you have to times that result by negative, because that j hat is special. So be careful. This is not the answer to part C yet. This moment vector is going in some direction, while the line OC is going in some other direction. What this question really means, the moment of the 10-pound force about the line OC, is they want the component of this moment that's in the direction of line OC. That's going to be this length right here. So when they say the moment of the 10-pound force about line OC, we calculated the moment about any point on that line OC, and the moment of the 10-pound force about OC is the component that's in the same direction as OC. So this moment vector here is this vector, and we want this length, this component. And to figure this out, we can use dot product. So, remember what the dot product between two vectors means. I take the x component of one, multiply it by the x component of another, the y component of one, multiply it by the y component of the other, and etc. And I add this all up to get some number, and that is equal to the length of one times the length of the other times the cosine of the angle in between them, right here. So we can manipulate this dot product equation to get this length that we want. Realize that we can just draw a right triangle in here. And what we really want, if we, here's our hypotenuse right here, the magnitude, the length of our moment. What we really want is the magnitude, that hypotenuse, times the cosine of that angle theta. That's what's going to be this length right here. And we can get this quantity because it's right here. all you have to do to get this quantity by itself is divide by the magnitude of OC on both sides of our equation. It's as easy as that. And because we're dividing this whole left-hand side by the magnitude of OC, the algebra will work out like this. And because we have OCX divided by the magnitude of OC, OCY divided by the magnitude of OC, and etc., another way of looking at this is that we have the moment vector dot producted with a unit vector in the direction of OC. Recognize that that is what this is. And that will equal what we want. So just know that a lot of books and a lot of teachers just teach you this. But really, if you just know dot product, you can manipulate the dot product equation and get what you want. I always like showing that all this stuff is just clever usages of the basics. So let's proceed with this plan. Before we do any of this, though, we need our vector OC. And I don't think we've figured that out yet. So let's figure out our vector OC. No crazy math needed. If I start at O and walk to C, in the X I've traveled 2 feet in the positive direction. So 2 I hat. And I travel 6 feet in the positive Y direction. So plus 6 J hat. And I don't travel up or down, so I have 0 in the Z direction. Okay, so we got that. So let's come back to our dot product plan here. I'm going to divide both sides by the magnitude, the length of the OC vector. Of course, we get a cancellation here. So now I have m cosine of theta by itself, which is the ultimate answer to this question here, to our part C. And now I just have to crunch this left-hand side. So we'll start with the sum of the products of our components. 0 times 2, 0. 20 times 6, 120. 0 times 0, 0. Add them all up, and we get 120, all divided by the length of OC. Well, we can figure that out by doing the Pythagorean theorem. Do some quick math here. 2 squared is 4, plus 6 squared is 36. 4 plus 36 is radical 40. So radical 40. So radical 40 right here. And that is what is equal to what we want. So if we crunch this number here, 18.97. And this is a moment, so units are pound feet. And the direction is in the direction of OC. So we don't want to break this up into I and J and K components because they wanted it about OC. So this is really in the, the OC direction, if you want to write it like that. So this is our answer to part C. So now the part D. The component of the 6-pound force about line OC. Same exact concept that we just did. We have our 6-pound force. There it is, going in some direction. We have line OC going in some other direction. And all I want is the component, the part of this vector here that's going in the same direction as line OC, which is going to be this right here. So, same exact concept. This is what the question wants right here. So just treat this thing like a right triangle and recognize that they want this will be the hypotenuse times the cosine of theta to get that adjacent side, which means we need to divide both sides by the magnitude, the length of OC to figure out what this product is right here. So we'll compute the sum of the products of the components. 0 times 2 is 0, plus 6 into 6, 36, plus another 0. So this will just be a big 36. And we already know the length of OC from last time. That's radical 40. And there we are. The component of that force F2 in the direction of OC will be 5.69 pounds. And of course, the direction of this is in the same direction of OC. So next we have to reduce the system of forces and moments, to a single force and moment at D. So remember, what this concept really comes down to is that we want to sum up all of our forces, and then we want to calculate the moment of each one of our forces about D, sum all these up, and of course add up all of the couple moments as well. So we're adding up all of the moments of all of the forces about D, as well as all of those free vector couple moments. So we'll add up all of our forces first. This shouldn't be too hard. We already have each one of our forces in Cartesian form. Also, these two forces, remember, these are those couple forces. They're of equal magnitude in opposite direction. So when we add these two up, they cancel each other. So they're basically not even there in terms of sum of the forces. So really, we just got to add these three up. And if we do that math, we'll get this resultant force here. So now we'll calculate the moments of all these forces about D and add them all up, as well as add up all the couple moments. Again, remember that these two forces are couple forces and form their own couple moment. So these two are basically already done. So, for the moment of force 1, about point D, remember we need an R from D to a point on the line of application of the force. So for force 1, I'm going from D to G. That'll be my R. For the next one, for the moment of force 2, about D, I'm going from D to B. That'll be my R. Here's our couple moment from the force 3 and force 4 couple pair. And for the moment of force 5, if you look at it right here, this force 5 is passing directly through line D. So I'm going from D to D, which is really 0. So I know that this moment is just one big 0. I mean, this force right here cannot rotate this object about point D. If you visualize that, you can't move in this box about D by pushing at D. It just won't happen. It's like saying I have a cylinder right here and I pin it right here and I try to rotate this thing by pushing here. It's just not going to happen when you push at that the hinge point. Okay, so we really only have to calculate these two moments here. I will erase all of this stuff. And of course, we can't forget that we have to add up our other couple moments that were there from the beginning, couple moment 1 and couple moment 2. Alright, so let's just set up these. Alright, so let's nail down our vector from D to G. From D going to G, I'm really just moving in the negative y. That's really just it. And I'm moving -6 feet in the y direction. So 0 in the x, negative 6 in the y, 0 in the z. Of course, I got my force 1 components in there. Now for the moment of force 2, my R is from D to B. So from D to B, looks like I'm only walking in the negative x direction, and that's it. So from D to B, I'm going 2 in the negative x direction, 0 in the y, and 0 in the z. And of course I got my force 2 components as well. So I just got to crunch these cross products here. They don't look too bad with all those zeros in there. Alright, so I'm going to just take a moment and make sure you're following that math. Alright, so we finally compiled all of our moments, our couple moments, as well as the moments from the forces that produce moments about D. Of course, now we just want to add them all up. So we want to add these 5 moment vectors here. So if we add up all the components from these moment vectors, we will get these following components. So that is it for part E. We've reduced the system to a single force and a single moment at D. So, part F. Can the system be reduced to a simpler system? And by this, I think he means a simpler system as in just one force. Can this system of a resultant force and resultant moment be reduced to just one force? And we can only do that if these two vectors, if the angle in between them is 90 degrees. So of course we can use the dot product for this. If the angle in between these two vectors is 90 degrees, cosine of 90 is one big 0, which makes this whole thing 0. So we'll do the math on this left-hand side, and if it's equal to 0, then we know that this angle must be 90. So I'll do that math, of course. So 0 times 80, one big 0, plus 13.6 times negative 13.2. So negative 179.52 plus negative 7.5 times negative 12, and that is a plus 90. So obviously the sum of this will not equal 0, which means the angle in between these two vectors is not 90 degrees, which in turn means that no, the system cannot be reduced to a simpler system involving just one force. Alright, pretty long exam review problem right there. Hope it made sense. If it didn't, feel free to ask any questions you may have in the comments.